which is find VC of infinity. So to do that, we'll draw it at time equals infinity. And when we're working up at those times, we know that that's DC steady state. So in DC steady state, capacitors become opens, inductors become shorts, and there are no switches. They all simplify to, well, in our case, this V sub S is 6 volts.
Could you explain, sir, why it's 6 volts, but when time is less than 0, it's 3?
Sure. Let's go back to our other. Do we have room to write that in our other board? No, not really. All right. So I'll put a little aside.
I saw it under the procedures PDF that you let out, and I just
Sure.
I never got quite clear.
So
why.
the question is, why? What does this thing look like, right? And the answer is that U of t. Sabine, what's U of t for time less than 0?
It would be 3.
That's just U of t alone?
Or no, U of t when time is less than 0, it would be 0.
That's right. So let's analyze this for time less than 0. U of t you just said is 0. 0 times 3 plus 3, what does that equal?
It would equal 3.
Yeah. So for time equals 0, wow, that's the worst line I think I've ever drawn in my life. For time less than 0, it's a constant 3. What is it for time greater than 0? What's U of t for time greater than 0? Just U of t.
It's at 0. It's at 0. It's 0. But
I only care about for time greater than or less than. So what is U of t for time greater than 0?
Would it be infinity?
No, you're getting confused with a unit sample impulse. What a U of t is it's something that's 0 for time less than 0, and it's 1 for time greater than 0. It's a unit step.
Okay.
So given that, now U of t for time greater than 0 is 1. So what's this whole thing become?
6.
6.
Okay, that makes a lot more sense. Thank you.
So for time less than 0, we draw it as a 3-volt source, times greater than 0 as a 6-volt source. Okay. Armed with that, let's do the analysis. This looks an awful lot like what we did before when we took a look at, when we summed our voltages around this loop, because we want to find what our V sub C is here. And when we do that, was that the end of our class?
I think so.
All right, I'm going to continue this on, and then I'm going to post this in the as a video, and you're welcome to look at it in the video. I love your questions. It just took a little bit longer than we thought. You're welcome to go now, but if you want to stay, let's finish the analysis. So we're going to do the same thing as we did earlier to find V sub naught. We're going to sum these voltages up, and we're going to notice that because this is an open, this voltage has got to be 0 volts. So doing a KVL around the green loop, we get minus 0 plus VC plus, we know there's no voltage ever across the inputs of an op-amp. That's, if there was, and there's negative. That's embarrassing. So what I've done wrong here is I've drawn this with positive feedback, and there should be negative feedback. I drew it correctly on the other page. So there's negative feedback. So if there was anything other than 0 volts across it, this thing would, the output would swing wildly to force this voltage to contract to 0. And we're left with plus 6. And by KVL, that has to be 0. And so therefore, we know that VC, which is really, since we're in DC steady state, I could have more properly written that as V sub C of infinity is equal to minus 6 volts. And all that is our third step.